So today we're going to be talking about how we get the area of an ellipse through this equation, and also the relationship between the area of a circle and an area of an ellipse. So first of all, we want to put this in terms of, well, we'll solve for y. So we're going to first off go ahead and do y equals b over a to the square root of a squared minus x squared. So now that we have this equation, since the ellipse since an ellipse is symmetrical, this part is going to be the same as in each quadrant. So what we're going to do is, so it'll be easier, we can just take the area of a quarter of the ellipse. So it would make it look like this. So right here, as I just said, it's going to go ahead and say that we're only taking a quarter of the area, and then later on in the equation we can just multiply everything by 4 since everything is symmetrical. So our next step is we're going to put it in the form where we can use trigonometric substitution. So we're almost there because we have this radical of a squared minus x squared, but we just have to clean it up a little and move the 1/4 over. So it would equal and we're going from a to b, or 0 to a, so we're going to go ahead and put the integral of a squared minus x squared. So now that we have it in the correct form, so we could use the substitution, we also know from the identities that it's going to go ahead and equal a sine, x is going to equal a sine theta, and we can just go ahead and do d of x equals a cosine theta. So that's going to help us when we go ahead and do the substitution. So we can go ahead and do that right now. So this part right here will equal, we're going to go ahead and plug in x right here. So what we're going to have is a squared and a sine theta, we're going to put it right here for the x. So we're going to have a squared sine squared theta, the square root. And then we can go ahead and simplify this a little by factoring out an a squared, which would give us 1 minus sine squared theta square root. So our next step is, now that we have 1 minus sine squared theta, that is also another identity, and which says 1 minus sine squared theta equals cosine squared theta, which corresponds to x equals a sine theta. So we can go ahead and write a squared and then times cosine squared theta. And then once we take the square root of this, we are going to get a cosine theta. So this right here, a cosine theta, is going to replace this. So we have the area of an ellipse equals 4b over a from 0 to a. And we have a cosine theta times d of x. So we're going to have a squared cosine squared theta. So now what we're going to do is, since we're solving in, right, from here to up here, we're solving in terms of x. Now that we have the theta, we got these limits have to be in terms of theta. So we're going to go ahead and change the limits of integration. So to do that, first of all, we can go ahead and move this a squared over here. So it would make it a equals 4b times a from a to 0 cosine squared theta. So right here we're going to go ahead and change the limits of integration. Like I said, for the purposes of putting everything in terms of theta now. So as x equals 0 and then x equals a, we have a sine theta equals 0 and a sine theta equals a, and that gives us sine theta equals 0 and sine theta equals 1. Inverse sine of 0 is going to go to give us theta, and inverse sine of 1 will give us theta. So the inverse sine of 0 is 0, and the inverse sine of 1 is going to go ahead and be pi over 2. So we have 0 and pi over 2, and those are our new limits. So we have a, the area of the ellipse, times 4ba. Now from 0 to pi over 2, so now that's in terms of theta. And now we have cosine squared theta. And here we approach one more identity. Cosine squared theta is a half angle identity, so we can go ahead and replace that, which will give us the area of an ellipse 4 times BA from 0 to 2, and then we have 1/2 1 minus sine theta is 1 minus so it's 1 plus cosine 2 theta. So this 1/2, we can go ahead and move the constant out to clean it up. And so now we have the area, 4 times 1/2 is 2 times b over a. And again at the limit of 0 to pi over 2. And now we have of 1 plus cosine 2 theta. So here we can go ahead and take the antiderivatives of 1 plus cosine 2 theta. So that's going to give us area equals 2BA from 0 to pi over 2. And the integral of 1 is theta. And then we can go ahead and use u substitution to find cosine 2 theta. So we can go ahead and let u equal 2 theta, d of theta. D of u will equal 1/2 d of u, to get rid of the 2, would be theta d of theta. And we have, that would give us 1/2 sine 2 of theta. So now we can go ahead and evaluate this at 0 to pi over 2. So pi over 2, we'll go ahead and start with 0. 0, plugging in 0 will give us 0 plus sine 2 times 0. So sine of 0 is 0. So pi over